Hello everybody, this is Josh Price and this will be the first in a series of lectures of how we deal with two-state protein folding equilibria, especially when it comes to fitting our data that we get in the lab. So with that, I'm going to switch over to Notability so we can draw together. The important thing to define at first is what we mean by a two-state protein folding equilibrium. This is a model for protein folding where you consider that the protein has an unfolded conformation in equilibrium with a more stable folded conformation, and that folding proceeds through a single transition state from unfolded to folded conformation without there being any intermediates. And in the simplest case, what we would be talking about is an unfolded monomer adopting a more stable folded conformation. All right. And the equilibrium would be defined by the difference in free energy between the unfolded and the folded conformation. So we would call that delta G for our folding. Of course, if you were interested in folding kinetics, that is how fast folding happened, you would be interested in this number, which we would call delta G double dagger. That is a energy of activation for the folding process. This regular delta G controls equilibrium constant through the familiar relationship that you learned in general chemistry. And in contrast, this activation energy governs kinetics or speed of folding. All right, so this is the two-state protein folding model. You go from, we'll say, an unfolded conformation, really an ensemble of unfolded conformations, to perhaps the more structured native state that you would observe in a crystal structure or NMR experiment. And we're going to talk about how you assess protein folding and how you fit data to determine what this delta G number is. But for now, let's just set up the theoretical work. Let's do the theoretical background work that will allow us to fit the data later on. All right? So first we need to define a few things. We've said that the free energy of folding is equal to minus RT ln K, where R is the gas constant, T is temperature in Kelvin, ln is natural log, and K is the equilibrium constant of folding. Another way to express that would be K equals the exponential of minus delta G over RT, where exponential just means the number e raised to the power of what's in parentheses. Okay? Now, in order to use our folding data that we might get from various sources to determine delta G, we need to find a way to deal with how the concentration of the unfolded conformation versus the folded conformation might change as we change equilibrium constant. For example, you might imagine for a lot of proteins that as you increase temperature, the difference in stability between the folded state and the unfolded state goes away to the point at which the protein unfolds spontaneously. So we need to have a way to model that. So we're going to begin with an unfolded state in equilibrium with a folded state or conformation, and that equilibrium is governed by the equilibrium constant, which we're going to say is also equal to the concentration of the folded conformation over the concentration of the unfolded conformation. We're going to put a few constraints on the process here as well. We're going to say that we know what the total peptide concentration is, because that's the amount of peptide or protein that we put in solution when we're doing our experiment. So that's a number that we know, that's constant. And we will say that the total protein concentration equals the concentration of the folded conformation plus the concentration of the unfolded conformation. In other words, all of your protein exists either as the folded conformation or the unfolded conformation, no intermediates. Now we can rearrange things just a little bit. If we divide both sides here in this expression by p, we get 1 equals concentration of the folded conformation divided by p plus the concentration of the unfolded conformation divided by p. Okay? And if we now take this number and call that f for, and I'm not sure how we should, yeah, let's just use a lowercase f equals the conformation of the concentration of the folded conformation divided by the total protein concentration. We're going to call this the fraction of our protein that is folded, or fraction folded. And we can similarly call this number lowercase u the fraction unfolded. And if we substitute those in, 1 equals f plus u, or we can rearrange and see that u equals 1 minus f. Okay? So if we know the fraction that's folded, we also know the fraction that's unfolded, because the only two things we've got in solution are the folded conformation and the unfolded conformation, no intermediates. Let's go back to our expression for equilibrium constant and see if we can't tease out some more details from the relationship that we've got so far. So folded concentration divided by unfolded concentration. All right. Well, we just said from a few minutes ago that all we've got in solution is the folded and the unfolded protein. So if we know the folded conformation, we also know the unfolded conformation. So we could rearrange this to say that the unfolded conformation is simply equal to p minus the folded concentration. So let's go ahead and substitute that in. F here in brackets over p minus f. And then if we divide, we multiply top and bottom by 1 over p, we can rearrange this to fraction folded over 1 minus fraction folded. And then we can do just a little bit of algebra to rearrange this and develop an expression for fraction folded in terms of equilibrium constant. So k times 1 minus f equals f. K minus kf, equals f. So k equals f plus kf. Or k equals f times 1 plus k, or in the end, k divided by 1 plus k equals f. What this tells us is if you know the equilibrium constant, you can calculate k. Seems you can calculate fraction folded. Seems obvious, but this is a key relationship for the monomer folding and unfolding equilibrium. You can also derive this expression simply by starting with the definition of total protein concentration and then substituting in, based on the definition of equilibrium constant, the unfolded concentration should be equal to the folded concentration divided by k. And then if we multiply both sides by k, and divide both sides by p, we basically end up with the identical expression that we derived over here on the left. Okay? So, and then if we want to go a bit further, we could say, based on this relationship here, for the definition of equilibrium constant, we could say that fraction folded equals the exponential of opposite of delta G divided by RT over 1 plus the exponential of minus delta G over RT, which means, and this may follow obviously from what was above, if you know delta G, you can calculate fraction folded. All right, that is for a monomer. Now, we haven't talked about what fraction folded means and how we use fraction folded to fit data. We'll leave that for a future discussion. For right now, just understand that fraction folded is something related closely to what we measure.
Yep. You want to go? Soon?
Yep. So we measure something from which we can calculate fraction folded, and based on that, we can determine what delta G is.